Last class, we worked out a way to create a uniform electric field. We can do that with an infinite plane of charge. That's how we did it, okay? And we will typically see that as a plate capacitor, though. We don't typically have a single plane of charge. We usually like to have two because it is very easy to create a component that accomplishes that. Now, there's a lot of really great things you can do with uniform electric fields because when a particle is placed in a uniform electric field, it'll experience a constant force when it's in the field and therefore experiences a uniform acceleration, which means now we can open up to the whole slew of problems that come from the kinematic world. So that's neat. So we know how that force is going to look. Force is constant because the electric field's constant. The force of the particle on the particle is going to be simply the product of the Q times E. Now, I got something to say about this. I've been grading the homeworks here. And there's a couple things that are happening more frequently than I would like. Nanocoulombs is 10 to the minus 9 coulombs. 10 to the minus 9 coulombs. A lot of you put 10 to the 9 coulombs, which is a lot of coulombs. You don't want that many coulombs. So my advice to you is to not do that anymore. The second issue is you got to be mindful of what kind of charges you're working with here. If you're told proton or electron, you know it's the fundamental charge. Otherwise, you're going to be told a charge, or you have to solve it or something like that. But a lot of people are mixing up. They have protons and electrons, and they put some weird charge in there. I don't even know where that comes from. Or the opposite happens, and you just start assigning the fundamental charge to all kinds of things, even though it says in the problem, that doesn't do that. So anyway, just be mindful of that, because it breaks my heart to have to knock points off for that. It truly does. The acceleration on a particle, now we just did this on a homework about a week ago, so you're familiar with this, but you divide by the mass. No, I cannot give you more time to write down the slides. No, I'm not going to do that. The slides are on my webpage, and you just can get the slide information from the webpage. You shouldn't be writing down anything on my slides. I mean, take notes is fine, but the slides are on my webpage. So, sorry, I'm not going to slow down to write stuff. The acceleration of the particle will be given as the force over the mass, which if we put in what the force is QE over m. Now that m, again, be careful. Protons have a mass and electrons have a different mass, and otherwise you have to be told a mass. So our acceleration in our problems, if we, for example, we do things kinematically, you could substitute for the acceleration with this expression here, QE over m, assuming you know your electric field and with the charges and things like that. Let's just jump right into our problem. Let's just get right into that one, which is right here. I'm assuming you can see that. Yes, you can. Oh, come on, Zoom. Not nice. All right, so we have two 2-centimeter diameter discs that face each other, a millimeter apart. That's that 20-to-1 ratio I was telling you about. So this is establishing a uniform field. They're charged to plus or minus 10 nanocoulombs, so one's got a negative, one's got a positive. Thus, we have a parallel plate capacitor. We want to shoot a proton from the negative disk toward the positive disk. At what launch speed must the proton have to just barely touch the positive plate? Well, we should be doing this with energy. but we're not. So let's do it with kinematics. It's a better problem for energy, but whatever. It's fine with kinematics. So now, in order to figure this out, we have to know what kind of acceleration the particle is going to experience, right? And we know what that is now. It's QE over M. What's E, though? We're not given E. Well, last class we figured out how to calculate the electric field due to a parallel plate capacitor. And that's the expression you see down here, eta naught over epsilon naught. Eta naught is the surface charge density. So that would be the charge on one of the plates divided by the area of the plate. When you do this, you look at, it's a parallel plate capacitor, right? And so the expression eta naught over epsilon, it takes into account the fact already that there are two plates. So the Q and the A is the Q and the A of one plate. So you put the 10 nanocoulombs there, and you put your area in there. Okay, so this is going to be Q over epsilon naught times pi r squared. Now, okay, we've already went on about using meters or not using meters, right? And we were all, well, I was, and a lot of you were down with let's do meters because that's the way you do things. That's right. The other thing that happens quite a bit, and apologies for this, but we're always giving you diameters. Always giving you diameters. And it's such a minor aspect of the problem that's very easily overlooked. But realize that you got to use radius, right? I mean, if your area formula is in terms of radius, you don't be one of those weird people that use the diameter formula for area. Okay, it's just weird, you know. So don't do that. I mean, you can, but yeah, nobody likes those people. So, all right. So we put in our expression here. We got 10 nanocoulombs, 10 to the minus 9. We got our epsilon naught in there. We got pi 0.01 squared because it's in meters, and we end up with an enormous electric field. 3.6 times 10 to the 6. Now we'll ignore for the fact that we're going to basically ionize the air and probably potentially hurt people in the vicinity of this, so let's not worry about that. Let's just go with this value here. We've now established our electric field, and that means we have now established what the acceleration is. So I'm going to go right into the kinematic equation, though. I mean, you can go ahead and calculate your acceleration right off the bat here. I'm not going to do that because I tend to like to put all my equations together before I do anything else, which I kind of didn't do here because I could have thrown in all this Q epsilon naught into the expression over here. Probably should have did that, but whatever. So the kinematic equation, the idea is that we're going to shoot the proton. It's going to experience an acceleration that will make it slow down. And so the idea is that if it barely reaches the positive plate, it will have a final speed of 0. So we have 0 equals initial speed squared plus 2a delta x. So the acceleration here is negative, by the way, just to be clear about that. So when I rearrange things here, you're like, where's the negative? Well, the acceleration is already negative, so the negative cancels with the negative. So I'm just doing magnitudes here. That's it. So I've got a question. The R in the electric field corresponds to the size of the plates. Size of the plates. Yeah. Because if you remember, for a parallel plate capacitors, the electric field is uniform regardless of distance. So there's never going to be a distance that you'll see for capacitors until later when we do something else. But for now, we know. I mean, when we do electric potential, we have to think about the distance between the plates. But it does not affect their electric field strength. That's different. Okay. I think my cat was about to assassinate me, but then I turned around at the right time. Woo! All right, so no. So if you remember those questions, do we need the area for both disks for the electric field formula? You do not. It's already taken into account of, because if you remember the electric field of a infinite plane, right, is eta over 2 epsilon naught. When you got two plates in there, the 2 goes away. So, and that 8 over epsilon naught refers to one of the plates. So, yeah, the Q is for one of the plates. Obviously, it has to be, right? Because you can't, if you add up the q's, you always are going to get a 0, so it doesn't make any sense, right? But the area is one plate. One plate. Excellent questions, people. Excellent questions. All right. So we solved for our initial speed. I'm going to put in my stuff for... Oh, I did do that. In a way. Yeah, I did do that, sort of. I put in the electric field stuff. I have a proton, right? Fundamental charge. I have... Oh, thank you. And... all right. I have a... Put the rest of my soda in there. That's nice. Okay, so we put in our numbers. Mass of the proton, fundamental charge, the distance between the plates, 0.001. We end up with a speed of 8.3 times 10 to the 5th meters per second. It's pretty fast. A little under 1% the speed of light. A little bit under that. So that's a great problem. Any questions about this problem? Fantastic. Moving on. It's a good lecture today, people. I'm excited because we're about to get into Gauss's law. And I'm feeling all tickled inside talking about Gauss's law. I want to just, I can't wait till next week. Put it that way. Put it that way. Maybe you're excited too. Question for you. Proton is moving to the right in a vertical electric field. A very short time later, what will the proton's velocity be? Letter in the chat, por favor. C's, B's. C's, B's, C's, B's. Aw, poor D. Nobody wants D. So sorry. I feel bad when I make the ones that are just really wrong. Asia, come on, get out of here. It's not D. Not D. Well, a lot of B's and C's, right? The answer here is going to be C. Now you say, what's the difference? Atom. Come on. All right. What's the difference between B and C? Okay, so in this question here, this particle experiences a vertical acceleration, not a horizontal one. So its horizontal speed should not change. That means if you look at the vector in B and the vector in C, the question you ask yourself is the horizontal component unchanged? And that's true in C, but in B, it looks like that horizontal component shortened up a bit, which should not be happening. That's why it's C. If you remember back in 110, we do kinematics. We separate the directions, and we solve the directions independently, and then we combine them later if we want to get an overall magnitude. Okay, but if there's no acceleration in the x direction, speed in the x direction should not change. Now, the vertical component, I mean, they show different vertical components. Well, I mean, we don't know what the electric field strength is. I mean, it could be any length. I mean, they show a length up here, but well, it could be anything. We don't know, right? Because we don't know what the strength of the field is. So the actual length up there is a bit arbitrary. All right. So, which electric field is responsible for the proton's trajectory? It's another good one. Another good one. Letter in the chat. Oh, I'm excited to see what you have to say. C's. Got a D in there. Got some C's. A lot of C's. A lot of C's. I'm liking C quite a bit because it is the right answer. So, when you look at this parabolic trajectory, now you know about parabolic trajectories, right? We did this back in Physics 110. This is how gravity works, right? And how you get a parabolic trajectory is you have projectile motion, meaning you have acceleration in one direction and not in the other one. So you can see that because there is symmetry in the path, right? The trajectory has symmetry. It's symmetric about a horizontal axis, which means there's nothing going on in a vertical direction as far as acceleration is concerned. If A or B were to be right, which would not look like a parabola. It would be speeding up as it goes down. C is purely changing, well, C is slowing the particle down, making it stop, and then having it move down. So there's a constant speed in Y, and there's an acceleration in X. So, to remind you of those things. All right, so let's do this problem here. You might remember this problem from a few weeks back because I basically did this problem as a means of review. But now we can formally, do all the E&M stuff that we just sort of glossed over in that example. Let's look at this one. All right, so we have an electron. Okay, so you see the word electron, right? Fundamental charge, mass of the electron. Got to make sure you keep track of those things, right? Mass of the electron, 9.11 times 10 to the minus 31 kilograms. Fundamental charge, 1.6 times 10 to the minus 19. So we launch at a speed of 45 degrees with a speed of 5 times 10 to the 6 meters per second away from the positive plate. So how will this thing behave? Well, it should go, the electric field is it's going to cause this thing to go up, right? The electric field here is pointing up, okay? The electric field points up, away from positive towards negative. But that means the acceleration is down because the charge is negative, right? So it's going to have a parabolic path. This is just like a gravity problem, right? So we know what our we have our electric field. No, we don't. Wait a minute. Oh, we got to find the electric field. Okay, that's nice. So our acceleration is going to be EE, it's lowercase e, fundamental charge, capital E, electric field divided by the mass of the electron. Fantastic. And then what we're going to do is we're going to put that into kinematic equations. We have a lot of information about the motion, so let's go through this. Now realize that the speed that's given is the launch speed. That's the magnitude of the vector. We have to put this into components in order to do this correctly. So the components are simply that speed times cosine and sine respectively, 45 degrees. If we look at the x direction, there's no acceleration, so we only have one kinematic equation that is of interest, and that is that the distance traveled is your v sub x times delta t. How long is delta t? Well, however long it takes to go up and come back down. We don't know that yet. We'll figure that out in a minute. Or do we? I don't think we need to know that. Anyway. For the y direction, we need something that involves acceleration. Yeah. We have the speeds of things here. So I'm going to go with equation 1. And I'm going to figure out the time in equation 1 and then put it into the x equation. Okay, so I'm going to use equation 1 that has the final velocity equals the initial velocity minus at. I put the minus in here ahead of time because the acceleration is downward here. Now the idea with the projectile motion is that whatever the speed was when it launched in the y direction, right? If it's a constant acceleration, when it gets back down to the same height, it's traveling with the same speed but downward. So this is a minus v y sub I here. And that goes in here. So then we end up with this expression right here. 2vy sub I times equals the acceleration times time. I'm going to solve for the time and equate the x and y directions together. And then I get this really nice proportion here. Okay, these are both the delta t expressions. One for x, one for y. That's the only thing you can mix together, remember, in x and y equations. The times are got to be consistent. Okay. So we solve for our acceleration. Our acceleration, we already know how to put that. It's in terms of the electric field. We have all this information here, fortunately. And we're just going to put it all together. So now what I did here, though, just to be clear, is the velocities. You see these velocities here? They're identical. They're not because of the 45 degrees, they're the same. So you'll notice here that I had a v sub x and a v sub y. I just turned that into v. But that's the V that has the cosine and the sines in it. But they're the same value. It's not the 5.0 times 10 to the 6. It's 5.0 times 10 to the 6 times radical 2 over 2. Or no, times divided by radical 2. I mean, no, radical 2 over 2. Sorry. 0.7. All right, anyway, solve for the electric field. 3.6 times 10 to the 3 newtons per coulomb. Fantastic. We know what the smallest possible space between the plates is. What that is basically when the particle shot up, what's the highest it can go without actually touching the tops. So the idea is that when you do that, we set that speed equal to 0 at the top. So it's all y direction stuff. So it shot up, and we want the speed when it reaches 0. That speed 0. So I'm going to use equation 3 here. I have my final velocity equaling 0. So I move my initial velocity over here. Again, the negative sign is already taken into account here. And I just solve for my distance d. The distance d is the height here. And I get 1 centimeter. So, given the problem here, it goes up 1 centimeter, comes back down. So I can make the plates closer together, as close as 1 centimeter. If I can make it any closer, there's enough energy for the electron to hit the plate. Now, it doesn't change the field strength, though, right? If I move them closer together, the field does not get stronger. The field is basically dependent on one thing, surface charge density. If I move the plates around, the only thing that would actually be affected is that if I move the plates, far enough apart, then my approximation of being a uniform electric field is not going to hold up anymore. Okay. And again, the advice the general mathematical consensus is you want your plates to be 20 times larger than their separation, usually, and then you can be pretty sure that in between the plates things are going to be uniform. It could be a little worse than that, but all right.
Oh. Mr. McGovern.
Yes.
Could you go back to that example real quick?
Yes.
Because I had a question for when you're solving the y direction with equation 1.
Yeah.
Could you explain why the final velocity is just the negative of the initial velocity?
Right, because it gets shot up initially, right, with the speed of 5 times 10 to the 6 sine 45, right? It's shot up. Now, what you learn in 110 in projectile motion problems is that the acceleration it experiences doesn't change, so it goes up to a certain height, comes to a stop, and now it's going down. Now, these are vector quantities, so if the speed's negative, you got to include a negative sign, but it will have the same speed on its way down that it did going up.
Okay, so it wouldn't be 0?
No. For this first part, we're considering it going up and coming back down. And it's not 0 when it's coming back down. This is, again, we're not considering it actually hitting the plate, because if it hits the plate, there's a whole different acceleration going on. There's a whole other problem going on there. We're considering the moment right before it hits the plate, so it still has a speed to it.
Oh, okay.
Right.
All right, thank you.
Yes. Yeah, if it actually hits the plate, well, that's a whole other problem, right? We'd have to know something about the interaction there. We have to know something about the recoil speed. Maybe we have to know the amount of time it was in contact, that we have an impulse problem to do. It's interesting, but beyond the scope of what we want to do right now. Let's move on to dipoles. All right. Topic number 2, dipoles. So, in a uniform electric field, what's going to happen to a dipole? Well, there's no translational motion, right? Because the two charges in the dipole are going to experience the exact same force, but in opposite directions. However, if the dipole moment vector is at an angle with respect to the electric field, then while the forces are the same, there is going to be a torque that's exerted on them, as you see in the picture here. And that will cause it to rotate. So that's something that we'll need to consider here, the rotation of this. If, as I mentioned here, if you have a situation where your dipole's moment vector is aligned with the electric field, then you don't have either rotational or translational motion. You don't have either of them because there's no angle there. So it's pulled and there's no moment arm to speak of here. And so that particular one is in equilibrium. But, do you have a question here? Well, I guess I'll talk about it later. All right, question for you here. Which dipole experiences no net force in the... Uh-oh. Uh-oh. Check in here. I see ADBC. Ooh. Uh-oh. We don't know what's going on here. The answer here is D. Right? No net force. No net force. You have the same magnitude for your positive, negative charge. No net force. Uh-oh, different question now. What experiences no net torque? What experiences no net torque? That's a different question now. So what do you think about that? Go look ahead here for a minute. What's the day today? The 9th. I got my dipole stuff. All right, that's good. Okay, fantastic. Oh, we're quick. C, huh? Okay, it's C. However, look at C, right? Check C out there. Is that the same as this? Okay, again, look at this one here. Okay, no net torque here, right? And then look at C. Are they the same? What do you think? Chat, speak up. Are they the same?
Not exactly, but they're still in equilibrium, right?
They're not the same. They are in an equilibrium, but there is a difference between these. And this relates to a homework question that you have. The difference between this thing here and this thing here is that the positive charge, okay, is oriented on the same side as the electric field points. Okay, so the negative is toward the downstream, so to speak, and positives towards the upstream. This is flipped around. They are not the same. What if I were to take this dipole here and nudge it a little bit? Just knock it up a little bit. What is it going to do? It's going to oscillate, and if there's any dampen effects, it will just come back to rest. But what if I nudge this thing? If I nudge that, this is what we call an unstable equilibrium, okay? Because if I nudge it, then this thing's going to flip over, right? Because the positive is going to experience a very big torque here, because the positive is going to want to go along the electric field lines. Okay, this is equivalent of, I have a ball, and I put the ball in a bowl, and I nudge it. What's it going to happen? It's going to oscillate in the bowl, and then come to rest if there's damping effects. But if I take my bowl and I turn it upside down, and I put my ball on top and I nudge it, what's going to happen there? It's unstable. If you slightly nudge it, it's going to roll off the side, right? So that's the equivalent example here. So be warned that there is a difference here in how it will behave. So how do we characterize that? Well, I'm glad you asked. All right, so this is dipoles show up in a lot of different ways in a substance. The electric field is exerted in the presence of this substance here, and if the atoms are so inclined to do so, then we have a polarization where the dipoles line up you get excess positive charge on one side and excess negative charge on the other side. Not a capacitor. Doesn't quite act like that, although there is things that we're going to get into later called dielectrics that have that sort of behavior to them. Now, in terms of what kind of motion is going to take place here, we got to figure out what the torque is. And the torque is going to be, torque is, the way I usually teach torque is, it's the distance from pivot to the force application times the sine times the force, right? Well, we got two forces here, so there's a factor of 2 in here. This D is your moment arm, which is the perpendicular distance from the axle or the rotation point and where the force is located. And if you imagine a little triangle here, and I'll annotate this so you can see the triangle, you can see the relationship there. So if I were to use, this is the triangle here. I should set up more like this, I guess. So that triangle there, you can either establish the moment arm, which is the distance d right here, or you can just put it in terms of what I said before, 1/2 s sine theta. Both work just fine. But that would be your value for d, 1/2 s sine theta. That's the moment arm. Or you could just say 1/2 s is r sine theta. Same thing, right? The force is the electric field times the charge. Now, the 2's cancel out. The S and Q come together, and they have this. That's that new expression we developed back when we first talked about dipoles, which is the dipole moment P. And so we see our torque here is PE sine theta. Well, PE sine theta takes the form of a cross product, and so in terms of vectors, the torque looks like this. Remember, P is a vector that goes from negative to positive, and so what you do is you can cross P with the electric field. You take your fingers, align them along P, and you open your palm up towards E, and the way you curl your hands would be the direction it rotates. Your thumb into the page indicates the direction of the torque vector. But you can see here with the sine function, it's stable at 0 degrees, right? And it's also stable at, 180 degrees. There's no torque, right? We're going to get into energy later. When we do energy, okay, if you remember how to do energy, you have to integrate your force over a distance or an angle in this case, and we end up with a cosine factor. Well, there's where that difference comes between the orientations, because in one case, you have a positive potential energy value. In between, you have a 0, and then at the bottom of the cosine curve, you have a negative potential. So there's different values in the potential energy. Anyway, we'll worry about that when we get into energy, which is not this chapter. But in terms of forces, they don't look different. In terms of energy, they do. Put it that way. Okay. How will the dipole shown behave in the presence of the point charge? What's happening here? Got a point charge. Aww. Oh, we got it right. Mostly. Not everybody got right, but the answer is C. So this dipole is going to start moving over to the left. Why? Because this is not a uniform field now. And the net torque is, the net force is not 0. That's it. So point charges, they're hard. They're simple, but there's some aspects of point charges that are harder. Right, let's do this dipole problem here. We got a parallel plate capacitor. We got a triangle of charge. 2 positive on top, got some negative on the bottom there. And we got to figure out what this triangle is going to do. Okay? So this is a dipole because you have the same amount of positive as you do negative charge. There is let me just bring up this thing here. There is a moment vector, right? A dipole moment vector that goes from negative to positive. The electric field goes to the left here. So there is a 90-degree angle between the dipole moment vector and the electric field vector. So there's a torque exerted on this that's simply equal to P times Z, where P is Q times the distance between the charges, or the average distance between the charges. And so this thing will experience a net torque. So is the triangle in equilibrium? It is not in equilibrium. It won't move left or right because the net force is 0, but it will rotate. And then in equilibrium, will the triangle move to the right, left, or remain in place? Well, it will remain in place, but it will rotate counterclockwise. Okay, and again, if there's no dampen effects, it's just going to rotate, pointed up. It's going to flip, point down, point up, point down. It's just going to do this forever. It's going to oscillate like this. If there's a dampen, then it will eventually dampen down and take on an equilibrium where it points to the left. So that's a great problem. Okay. Fantastic. Let's push on. Topic number 3 of the day is symmetry. What I mean by a dampen effect, basically I mean like a friction. So the idea is if this was occurring in air, then there would be a drag term that would be produced in an acceleration that would slow it down. So every time it moves through a certain angle, it's going to start to lose energy. The term dampen refers to a couple things. The energy is being dissipated away. We refer to it as dampen. But if you actually look, and if hopefully you did this in 110, and I covered this very briefly for my class, but if you look at a sinusoid that's dampened, the sinusoid is sort of sandwiched in a exponential envelope. Let me just real fast bring this up because it's kind of a cool thing to look at. Let me see if I can do this fast. What the heck's wrong with my hair? Oh my goodness. All right. Where is it? Physics 110. Ooh, I think it's here. Is that fluids? No, it's not. So this is one of the very last things we do in Physics 110. Let me screen share this thing. Ooh, where is it? So now the equation of motion, was this fun thing down here. If you have drag, you have an extra term in Newton's second law, which means you got a second order differential equation, which in 110 you don't know how to solve that, but eventually you'll figure it out. We take differential equations. The solution to this is this damped oscillator. So you have a cosine factor, which is the oscillation, but then it's modified with an exponential decay. And so you get something that looks like this. It's sinusoidal, but it has this envelope that's exponential, and so the amplitude winds down. And that's what would happen if something's damped. It just winds down, put it that way. All right, that's lovely. We are not going to do any dampened stuff because dampened stuff is a second order differential equation at its core, and you don't know how to do that. I mean, maybe you do, but you don't. We pretend you don't. The highest math you have is what, fractions, I think? You guys have fractions? You guys cover fractions in 160? I think you do. So. Okay. No problem. All right, symmetry. Why do we care about symmetry? Because we're trying to make our life easier. Okay? What I basically did to you for the last couple lectures is show you how awful this stuff is. And maybe you felt that way. And if you did, well, I did my job. All right? Is that the only way we should do our problems? No, we can do our problems different ways. But you can't appreciate, the nicer stuff unless you have to deal with it, right? You build an entire house with a hammer because you can't appreciate the nail gun. until you built that one house with the hammer. Okay. But you're not going to be stuck with a hammer. We're going to be doing better stuff. So we have a different method that we're going to develop to solve electric fields due to continuous charge distributions. It's not Coulomb's law. Because Coulomb's law is what we refer to as a brute force method. We take an object, we say, well, this is not a point charge, but we're going to figure out a way to make them point charges. And so we break things up, and then we just sort of brute force, just add it all up. And that's fine, but it's a little more challenging mathematically. You can use the hammer to damage any of your devices if you're not happy with how you are performing in the class. That's not on me, that's on you. But otherwise, I don't think you'll need much of a hammer for that. If that's what you're speaking metaphorically still, and I lost you there. But no. Oh, maybe you're... Okay, let's say you're speaking metaphorically and I'm not such an idiot right now. When you end up taking your test, if I don't tell you to use a particular method to solve something, you can do whatever you want. Okay? So, like, for example, if you're just like, I can use Gauss's law for everything here on the test. If I don't say you have to use Coulomb's law, you can do whatever you want. Scout? Be quiet. Too loud. Yeah, sorry. I was a little dumb there. Okay. Thought you were making a little joke. You weren't. All right. So, Gauss's law, though, there is a lot of concepts. It's going to take some time to develop the ideas behind Gauss's law. Gauss's law is deeply conceptual. The mathematics is very... it's laughably simple, the mathematics. But to get to the point where you can use the laughably simple mathematics, you have to understand a lot of concept to develop the little bit of math that we actually have to do. And that involves really two things. One of those things is symmetry, and the other things are flux. So we're going to spend a bit of time today talking about symmetry and flux. And then the next class, which will be on Monday, we're going to talk a little bit more about flux, and then I'll end up showing you what Gauss's law is. All right, so when it comes to symmetry in problems, we are trying to look at how our charges are distributed, okay? Well, you'll see Gauss's law is pretty cool. We try to see how our charges are distributed because any symmetry that exists in our charge distribution has to match the symmetry of an electric field, okay? I'll say that one more time. Any symmetry that exists in a distribution of charge, okay, that same symmetry has to exist in your electric field, okay? Because if you were to take your distribution of charge and you were to do any kind of rotation, translation, rotation, translation, mirror flips and things like that, and your charge distribution doesn't look any different, well, how could your electric field look any different, right? So, like, for example here, we already know how to do this, right? This is an infinitely long charged cylinder. Well, it's basically a... Yeah, let me say it one more time. Scout, don't sing. Don't sing. I like singing, but I'm working, okay? All right. Sorry if you enjoyed this singing. Just got to stop. All right. So here's what I mean. Actually, you know what? Hold on. I think I'm going to say this again later on here. Yeah, you know what, Eric? I'll say it again. Give me through these slides and I'll be saying it again. All right, so there are three different kinds of symmetries we're going to work with here. This one happens to have what we call cylindrical symmetry. Okay, it's a cylinder. So like actual cylinders have cylindrical symmetry to them. Planes actually have cylindrical symmetry. Lines have cylindrical symmetry to them. So that's kind of helpful. Now, how do we know this? Okay, here's how you know this. Okay, so if we have our cylinder, say it's an infinitely long cylinder, there's a lot of things we can do to it that will not make it look any different, right? We can roll it, right? We can roll our cylinder. Do I have a cup here or something? I don't really have a... Does this have water in it? It does. Can I chug all this water? No, I can't chug all that water. Can I chug this thing? I don't want to do that right now. I don't have any. Whatever. Okay, just imagine a cylinder, right? Toilet paper roll, whatever. All right, if you roll it, it doesn't look any different, right? If I move it left to right, and it's infinitely long, doesn't look any different. If I cut it right through its middle, and I flip it, doesn't look any different. If I cut it perpendicular to its axis, and I flip it, doesn't look any different. Or if I not flip it, if I just look at mirror images. So these are all part of the cylindrical symmetry involved. Okay? So now, here's an example of what I was talking about before. Say we have this line of charge, and say we don't know what its field looks like. Right? We don't know what its field looks like. We're going to make some guesses, though. Okay? Now, the guess here is that the electric field goes up and to the right on this thing. Okay, that's wrong, but let's just guess it. How could we know that it's incorrect? Well, it's because, again, the field would have to have the same symmetry as the rod. Because if I were to say, to take this entire rod and to flip it around, right? Say I took my rod here, I don't know, like my soda bottle here, okay? Right? And then I flip it around like this, right? Now, assuming this is an infinitely long rod, if I just rotate it, well, does the rod look different? No, it doesn't look any different. If I were to roll it like this, does it look any different? No. So that means when you do that stuff and your field changes, because if I were to rotate the rod around, now the electric field doesn't point up and to the right, now it points up and to the left. And is that a different field? Yeah, that's a different field now. So could that be the field of this rod? No, it can't, because charge symmetry and field symmetry are the same. Okay, so this is not a good guess. This is not correct. This is not the field. Okay, so yeah, if I flip it around, the field's different, but the rod doesn't look different. So this cannot be a proper field. Okay, what about this one here? We're looking at the cylinder down its axis. And maybe this is the field, has some kind of weird rotational thing to it. Well, if I take a plane that cuts it vertically, and I were to flip it, or just look at a reflection, does the field look different on the left and on the right? Yeah, it does. The field on the left here doesn't look like the field on the right if I reflect things. So this is not right either. This can't work. Okay? So, like, we just did it here. Okay, we flipped it around, and that's not the same field. Those look different. So that's wrong too. This works, though. This works. And you've sort of already seen this. This is, you know, if it's a cylinder, it behaves the same way as a line does. So you've already seen this. It's radially away. Okay? There is symmetry here. Again, what if I were to flip the rod around? Is the field different? No. If I were to rotate, does it look different? No. If I do any kind of reflections, does it look different? No. So any way that you can rotate, reflect, translate the charge distribution, and if there's no difference in how it looks, then the field has to reflect the same thing. This is what we mean by symmetry. Very, very similar things when translations or flips or anything else are done. And so part of what we're going to get into is recognizing the symmetry in the charge distribution and having some educated guesses as to what our field might look like. And they are that. They are, in a way, I hate to use the word guess, because it's not like we're just coming up with, we have a very educated guess. And these will usually be pretty clear. Usually, I don't know. I've been doing this stuff for 20 years. To me, it's clear, but you know, obviously it's not always going to be clear. Okay. Yeah. All right, so there is the cylindrical symmetry. We also have planar symmetry. And that planar symmetry is just an infinite plane. And there's a lot of similarities, by the way, in cylindrical symmetry and planar symmetry. And objects can have both, by the way. Just because something has planar symmetry doesn't mean it can have other kinds of symmetries. It certainly can. Okay? So, but a planar symmetry is one where translations don't change anything. You could rotate things in the plane. That doesn't do anything. You can reflect things through vertical axes. That doesn't change anything. Okay. So then your field would have to, again, match that. And so we already know what the field is. It's directly away from the plane of charge. We have one more type of symmetry, and that is, I already said cylindrical symmetry. Come on. Why is this here? Spherical symmetry is the other one. Okay. So with spherical symmetry, if I were to rotate or reflect anything, it looks the same. Translational looks different, obviously. But any kind of rotation or reflections are always going to be, as long as they're through the center, obviously, right? They're always going to look the same. And so the field there is going to be radially away. It's just like a point charge, by the way. Just like a point charge. So, all right. So we got some coax cables here. And we have an inner cylinder with a positive charge and an outer cylinder with a negative charge. We want to draw the correct electric field vectors using the symmetry here. All right, let's do it. Now, you're still using the same principles we know before, that, electric field's got to point towards negative charges, point away from positive charges, so you need to be mindful of that. So if my inner cylinder has a positive charge and the outer one is negative, I'm going to draw that like that. The electric field's going to point radially away from the positive cylinder. And again, if I were to rotate things, reflect things, everything's still going to look the same here. And then the on-axis view shows, again, radially away vectors. Same deal. If I flip things, rotate things through the middle, if the charge looks the same, the field looks the same, and that means that this is a correct representation of the field, as long as I've taken into all the different symmetries into account. So we can go with this as our field. That helps us set up our Gauss's law, basically. That's why we do that. All right, so how do you do that? I did that. Okay, so now it brings us to the second concept. Not the second concept, the last concept. Concept number 4 for today. And that is the concept of electric flux. Okay, so have we done flux before? Well, yeah, back in 110 we did flux, we did fluids. Back when we did fluids, flux was, a certain amount of, say, water, goes through, a pipe of cross-sectional area A. It's an amount, usually over an area, or could be a volume, could be a rate of some kind. In astronomy, we have the concept of solar radiance. And that concept of flux is how many photons go through a certain area per second. That's the concept of flux, like when we talk about the brightness of stars and things like that. The way we do flux in this context here is we imagine the electric field passing through surfaces as a result of charges. And if we characterize how much electric field goes through a given surface, that is another concept of flux that we're going to do. In this example here, we have a box. Something's in the box. We don't know what's in the box. Well, we kind of do. But the box has 6 sides. We can see what the field is doing. The field is exiting the box. Okay? So because it's exiting the box, we sort of know what kind of charge has to be in there. There has to be some kind of net positive charge in there because electric fields point away from positive charges. Could there be negative charges in there? Yes. The idea is that the net charge, though, is positive. Okay. This would have a net negative charge on it. The electric field points towards a negative charge. We won't typically know how the charge is configured unless we have very detailed electric field information, which we do not have here. The illustration that's being shown here is simply indicating that there is a net amount of negative charge in that box. But without more information about the field, I don't think we can really tell what kind of distribution of charge we're going to have. If you're wondering about that, well, guess what we're going to do Friday? A little bit in lab on that concept, actually. Okay, excellent. What do you think's going on here? You got is equal number of lines going in, and you do coming out. And when that's the case, you don't have any flux, net flux, because your net charge is 0. So we're going to be very mindful of, we're going to create closed surfaces, boxes, cylinders, spheres, and we look at how flux goes in and out and through these things. Okay, our choice of our boxes, our closed things, are based on symmetry stuff. Okay, so now that we know the different kinds of symmetry we can work with, now we have to think about how the electric field is going to pass through all these different things. In this example here, it is 0. Okay, just as much electric field goes in as comes out. All right, so now look at this question here. You have electric fields going in all different directions, and what we're interested in here is a net flux. A net flux will reveal a net charge. So you have 6 arrows here. Consider all that go in and all that come out, and let me know what you think is inside that box. The answer, according, a lot of B's. I like it. All right, there are 4 arrows that go in and 2 that go out. Okay, the arrows are the same length, so we can assume that's the same amount of electric field. But if there's more arrows that go in that come out, then inside that box is a net negative charge. Got it. Good. All right, last example. I'm going to finish a little early. All right, let's look at what's going on in these problems here. What type of net charge does the box below possess? All right, what goes in, what comes out? What goes in is a 15 on the top, 15 on the front, 20 on the bottom. So overall, 50 newtons per coulomb of electric field go into that box. Now, by the way, just for future reference here, we treat fluxes that go into things as being negative, going out as positive, and that follows the convention of electric fields. Electric fields point away from positive. Electric fields point towards negative charges. So I'm not putting negatives in this example here, but you're certainly welcome to start doing that. You could say this is a negative 50 inward. Okay, negative 50 inward. Going out. On the left, 10's going out. On the right, 15's going out. On the back, 20's going out. So overall, 45 going out. We add them up. We end up with a net 5 nanocoulombs in, which means there is a negative charge in this box. Net negative charge in the box. It keeps using that word net. It's very important here. We don't really know how many charges are in there. We don't know how they're configured. We don't have enough information. All we can tell is that whatever's in there, there's more negative than positive. That's what we're going to say here. Okay, what electric field strength must be present through the front if a negative charge is inside, and in which direction? Okay, let's look at what we currently have, though. Going into the box, on top is 15, and through the right is 20, and that's a negative 35. I'll say it negative 35. What's going out? In the back, 20, on the bottom, 10, and on the left, 10. So 40 is going out. We want a negative charge in here. At the moment, we're sitting at a plus 5. At the moment, we're sitting at plus 5. So if 5 were to go into the front, it would be a net charge of 0. So we need a greater, if you get what I'm saying here, a greater negative, a more negative electric field. So whatever goes in has to be more than 5. Okay, more than 5. It's got to be in, and it's got to be more than 5. If it was 5, it would be a net charge of 0. And anything greater than 5 in would allow us to have a negative charge. Okay, great. That takes us to